We can.
Yeah,
Good.
cool, great. Okay, so I'll start. First of all, thank you everyone for joining today. Um, my name is Matteo de Martino. As Doug already mentioned, I work in the engines team here at Lenses.io, and the engines team is the team that work on all the tools that allow you to read, process, and manipulate data through SQL in your Kafka, Elasticsearch, and whatnot. So today I'm going to speak a little bit about streaming and SQL, how Lenses does it, and I'm also going to do a little bit of a demo for you. So as I mentioned, the agenda is going to kind of start from the beginning. I'm going to do a little bit of meaning. What does streaming mean in the context of streaming data in Kafka, etc. Then I'm going to briefly mention why SQL is talked in the same sentence. Why would we do this with SQL rather than other tools? And how does Lenses productionize this through on top of Kafka and on top of Kafka Streams. Finally, I will conclude, as I mentioned, with a demo, with a scenario, with a non-trivial query to actually see how the experience actually feels like. So let's jump right in, and let's start with the streaming 101. So let's start from very obvious, trite statement that data is everywhere and all the time, right? Everyone knows this. What I mean, though, is that really we have so much data that we sometimes, even the way we interact with it is very different depending on scenarios. And mainly you can see two categories of interaction with your data. Either being able to act on your data, basically something like what the database and analytics tool do, or react to signals coming from your data. So talking about the first category really is the most familiar way of querying data that you could have. The query in this scenario is active. You actively ask something to your database, Excel, spreadsheets, whatever. You actively do query something, you ask something of the state of the world, and the data itself in this context is quite passive. You have use cases that do this. Is kind of like analytics, modeling, data modeling, and basically it's everything that answers a direct question, right? In a synchronous manner. Most of the time, this is a synchronous model. So you ask, wait for the information to be ready, you consume it. On the other hand, the other side is a little bit, the reacting to data signal is a little bit less familiar, but I would argue equally important. And in this situation, the two kind of actors are flipped. The query in this situation is passive, because what you do in this situation is kind of like saying, I describe how I will react to something that might or might not happen in the future. So you're passive, you're just waiting and saying, I will be doing that sometime, maybe. And the data itself is active, because it's the data coming in that will, in fact, trigger the behavior of your query. So it's a little bit like flipped on its head. And as you can imagine, these kind of two approaches are, in fact, two faces of the same coin. In practice, acting on data is more understood and familiar, and it talks about the state of the data, state of the world. Questions like, what is the current my current account balance? And it is 10 pounds, right? It's about the state, and it's usually synchronous. You ask now, what is the current balance? And I get the answer. The reacting to data signals, on the other hand, is usually asynchronous, because you let it happen and as a stream of events. And it's more about the state change rather than the state. And most of the time it requires specific tools, because you don't have the same visibility on the whole system state, etc. We as humans think about state as a whole, and not necessarily of the single signal changes. So taking just a little bit of a step back on how we could use, where do these two categories fit? Let's think about time, right? We have the time continuum, because it's a fancy word, and basically we have present that divides the past from the future. Now, the category, the distinction between past and future is pretty obvious. The past is whatever data happened to arrive in the past actually already arrived. It's present. It's known. The past is the amount of data coming in the past is finite. However, might possibly be big. In the future, on the other hand, it's unknown, right? Data did not arrive yet. It possibly infinite. It might arrive. It might not arrive, etc. So you kind of feel that these are intrinsically two different approaches to data, and obviously you need two different tools. In lenses, these two tools are called engines, and we have two engines. We have a snapshot engine and a streaming engine, respectively, to handle data that is already present, asking synchronous questions to this data, and streaming engine that handles the shaping of a blueprint for processing in the future. And these tools are productionized in lenses via two features of the product that are called SQL Studio and SQL Processor. SQL Studio, you might have used it to query on the spot some data that is already in Kafka or in Elasticsearch or whatever. And as in streaming, the SQL processors is what you set up to react to events. Today, we're going to focus more about SQL processors. Now, what is all about this streaming data in Kafka? What does it mean, streaming data in Kafka? So basically, as I previously mentioned already, is basically modeling, transformation, and processing of streaming data. By streaming, in this context, we mean that it's infinite amount of data, potentially. It needs to be able to work on infinite amount of data. And it's designed, and this is an important point I will come back later in the future slide, it's designed, the frameworks are designed to work on data that is already in Kafka, or that will be in Kafka by the time it's processed, and to write it back in Kafka. This is an important point. I'll come back to this later. And the kind of transformation and processing that needs to be supported are things like multiple input records, creating a single output record, aka aggregations, multiple output records coming out from single input records, aka explodes. A nest explode is usually called in other products, and also even more common situation where you create a single record from multiple data streams, aka joins. So these are the kind of processing and transformation that we need to be able to support. And how does Lenses do this? Lens productionizes this by exposing an SQL-like language to model such scenario in an as intuitive way as possible. It's built on top of Kafka streams. So it uses Kafka streams for its fault tolerance and elastic partitioning, etc. But it doesn't expose it to the end user, and therefore it doesn't expose its complexity to the end user. And it supports all the transformation that we mentioned earlier. It supports projections, aggregations, lateral joins, which is what we in Postgres call explodes and a nest. We support joins, etc., etc. And the cool thing about this is that it's integrated in Lenses. It's not an application that you need to figure out how to deploy or run. It's integrated in Lenses. Therefore, you have the ability to manage its life cycle, to monitor its metrics, to scale down and up as needed. And also, it's strongly typed. The streaming data in Lenses is strongly typed, so it will be able to catch situation where you might do some mistakes or try to do something that the data doesn't actually fit. So a little bit of a parenthesis here. Why SQL? I mentioned that I would explain why we would care about SQL in this context, because of course we have products that don't necessarily rely on SQL. For example, Kafka streams. Now, SQL, though, is very familiar. A lot of people have used it or will use it in their life, professional life, and really, this makes it a generic skill. SQL is a lot more accessible than a programming language. I give you that it's a lot less powerful, it's a lot less formalized, but it's more accessible, and therefore it might mean that you don't need to actually go and ask a team of software engineers to do a small application that you might yourself be able to do in half a line of SQL. And this is very powerful. Could save a lot of time and a lot of resources. Now, one final thing is that SQL really fits pretty well with most of the operation that we need to support. I talked about aggregation, joins, etc. These are all common SQL operations, right? We are all familiar with them. There is some semantic difference. I will start kind of briefly mention it, can't go into too much detail today. But besides those differences and what they mean, most of the SQL paradigm kind of fits. And finally, really, I mean, the market loves it. Even every product out there really have an SQL, and even products that were not designed and released with SQL were later enriched with SQL. Therefore, we said we need to have it from day one as a part of the design. So I will also just mention a little bit of the limitations in streaming data in Kafka, or maybe limitation is not the right word. Possibly design implications of Kafka itself is worth mentioning. The streaming application are non-integration points. This is what I was talking about earlier when I was saying that data needs to be already in Kafka, it needs to go back in Kafka. The streaming application are not meant to be sources or sinks between different systems. You wouldn't use a Kafka Streams application to write something to Elasticsearch or read something from files. You can, but there is a different product for that in the Kafka world, which is Kafka Connect, which is the integration technology. So there is some overlap sometimes between Kafka Streams and Kafka Connect, but we need always to be careful because these overlaps are a lot smaller than people sometimes think. Therefore, streaming is for streaming, integration is a different concern. Another thing that possibly is quite obvious, but it's worth mentioning, is that really, even if you're streaming data, it's not like magically you can do things you couldn't do before. It's still the same technology. It's Kafka underlying. You will not be able, for example, to create a high-frequency trading platform on top of Kafka Streams. The latencies are not there. The performances, it's not been designed for that in mind. So, of course, the technology is still, you need to use the right tool for the right job. And finally, because of the nature of what streaming means, really, you wouldn't shape your transformation as something with a clear beginning and a clear end. It doesn't fit well with the model. So most of the time, your streaming data application will not really have a clear beginning and a clear end because they just react to events. There is no concept of beginning or an end in the stream of events. With this in mind, I have these slides with a few examples of good fits and poor fits for streaming, but really I'm just going to go through a couple, and I'll leave the slides. You will have access to it if you want later. So an example of a good fit for using streaming is something that if you have a requirement of every time a new event is received, take part of this event and process it and save it to another topic. That's a perfect fit, right? Because we are reacting to the new event coming in, we processing it, saving it somewhere else. It doesn't have a beginning, it doesn't have an end, it reacts to data coming in. On the other hand, if we were asked to find how many instances of items with a given name were sold yesterday by our system between 5 and 9 p.m., you can see that this is a perfectly reasonable query, but it's something that you would use a database usually to do, because you need the whole view of the whole system. It's a very synchronous kind of, I ask a question, check the data as it is right now, get back the answer. And this just doesn't fit streaming. This is just to mention the fact that you have cases that fit and cases that don't. Now, I will conclude this kind of introduction to streaming with a little bit of a technical side. I've been talking about semantics a while now, and I just want to start mentioning the two main abstractions of streaming data in Kafka, which are stream and table. Now, with that, it's a big topic. I'll try to be brief, but also complete. The idea here is that these two are abstraction that are based on how you interpret a stream of events. So a topic in its own right, by itself, if we don't add any further concept on top of it, represent effectively the abstraction of the stream. It's a sequence of events over a continuously changing data set where each event is independent. The stream itself is potentially infinite. The topic is potentially infinite, doesn't have an end. And each event, it being independent, means that the whole concept of a stream is stateless. You don't have to relate between events because they're independent. They are just signal. It's like bips from a sensor. This is usually also called in the literature record stream, and it's opposed to the other way of seeing a stream of events, which is sometimes called changelog stream. What a changelog stream is effectively a table, an abstraction code table, which is effectively interpreting every event in your stream as a key value pair that updates the current state of the system. So if you have a key value pair, it is effectively saved per key, and any new key value pair with a given key that was already seen will override the previous ones. So it's a stream of updates. It's a changelog stream. It's a stream of the change for a given set of keys. It's about the state of the world. It's effectively a database table. It's what everyone knows as a database table or a map if you're a developer. And it's a ways that Kafka streams and Lens's SQL processor give you to materialize a table, the equivalent of a queryable table from a stream. And it's usually backed by local storage, in the case of Kafka streams, by an instance of a RocksDB table that will allow to query things fast without having to read a Kafka topic. So why do I even talk about Kafka stream and table, and why do we care about this abstraction? Because they are really very much related to each other. There is a deep duality between the two, and I'm just very briefly mentioning this because it is the basis of important distributed system patterns, architectural patterns like event sourcing, and the basis of Kafka streams fault tolerance and partitioning as well. The idea is that from a stream, you can always get a table. And from a table, you can always get a stream. Not necessarily the same stream that brought you to the table, but you always can create a stream from a table, and therefore you can have this cycle. You can see it in this example, for example. You have a stream of events, which is moves in a chess game, right? From the start of time, you get to apply each of them in order. You get to a state of the world. This state of the world represents a valid configuration of the universe, right? Now, and this is a table, because if you get each piece as the piece is the key and the position is the value, you have a table, right? Which represents the state of the world. If I move a piece, I'm overwriting its previous position. Now, if this table that I have, I iterate over each piece and emit an event with its position, with the piece in its position, I effectively have a stream of current positions that if I read back as a table, again, I get the state of the world. You can see now that there is a cycle here. And this is important because you can effectively build your state from the events that made you get to that state. And that's the key of event sourcing. That's the key of how key tables are fault tolerant in Kafka, etc. Okay, so this was as brief as an introduction as I could give to streaming in Kafka and lenses. It is a good time now to kind of stop for questions or thoughts before I go into the demo. So if you have any thoughts or questions, please do ask.
So we have a question from David. Any gotchas while scaling K tables?
So what do you mean here by scaling? I'm assuming that by scale you mean adding partitions. What exactly do you mean by scaling here? Large number of rows. Okay, so basically the idea here is that in practice this is just like scaling any other topic, because a table is an abstraction on top of a topic. The fact that you read the topic one way or another doesn't change that. So in fact, if you have large number of rows, it still partitions that topic, right? And the partitions is will still kind of manage a set amount of keys each. It's down to your partitioner how well you're partitioning your data set. That's probably a separate question. But if you then have different nodes handling different partition, that's just going to work. Now, the fact that you have more rows really doesn't. The important thing here is not much the amount of rows. It's the amount of different keys. Because if you can have 1 billion different rows, all with the same key, and of course it's going to be one record in the table. Also, one thing I didn't mention: tables are actually backed by compacted topics, so they effectively a topic is read into the local storage, and this local storage is locally maintained as a compacted topic that represents the writing of the state. So in fact, if you have 1 million records, those are just going to be deleted. Only the last one is kept by definition what a compacted topic is. So you scale a K table just as well as you scale a compacted topic. Hopefully this answers your question. Do we need to consider, so I can see another question, do we need to consider plan for that with lensless SQL abstraction? We need to consider the scaling scaling concerns, and the answer is yes. Not just for your K tables, in general for your streaming application. In the demo, you will see that there is a degree of taking this into consideration. If you have a topic with 1,000 partition, you probably will want to deploy it and have it running in multiple nodes, so that, for example, each single node can handle just a subset of this partition, and therefore you can scale out. And maybe you just know that the distribution of this partition is one way or another, and you can assign it one way or another. That answer, okay, yeah, cool, my pleasure. Cool. Okay, in that case, unless there is anything else, I will proceed with the demo.
Sounds good.
Cool. Okay, so our demo, as I mentioned, what we're going to see in this demo is basically how Lenses does streaming SQL, and this is, as I mentioned previously, we call it LSQL processors, L for Lenses, of course. We're going to see some initial examples of what is possible to express with our syntax and what is supported by our engines in the streaming context, as well as we're going to see and feel how the integration in Lenses enables us to manage things like log management and deployment in Kubernetes, and therefore that scaling concerns can come into the picture. So let's see, you should be able to see that now I flipped to Lenses. Yes?
Yep, looks good.
Okay, cool. So in Lenses, you can see that I actually didn't mention this. I can mention it straight away. We're going to create a topic. We're going to simulate. Actually, let's go back 1 second to our demo. Let's introduce what we're actually going to demo. The idea here is that we are a company developing self-driving cars, right? Very fancy nowadays. and we are in our research and development phase. Now, in such a phase, it's normal that we want to gather as much data as possible and send it to potentially to our data analysts in the cleanest possible way and in as fast as possible way, so they can do their job and improve our product. Now, the data that we're going to work with is going to have this shape. The key of a record is just going to be some random string, some random ID. The value is going to look something like this. So we are going to have an ID for a car, some information about the speed, some information about the sensor. A car might have multiple sensors, optional latitude, optional longitude for that sensor, and some event time, right? Now, a few things about this could be improved or could be made more useful in light of giving this to downstream. One thing I can think of is, for example, the key shape could be more useful. At the moment, it's just a random string. We could see that the downstream system care more about a car ID and maybe the composite key of a car ID and a sensor ID. Another thing that we could do is do a favor to our European colleagues and save them a Google search. Instead of having the speed in miles per hour, we could also add the speed in kilometers per hour. So we save them a Google search. That's just it's been a bit of a kindness. Another thing we could do, so these are self-driving cars. We don't want these cars speeding. And sometimes maybe the algorithm had a glitch and they went too fast. We want to have a flag that is very clear for the downstream system to when that happens. Other things could be we want to clean our records. Maybe the location sensor is a bit glitchy. Sometimes it doesn't report the location, and we want to remove records that don't have a full location, or records that come from what maybe we have some test cars in our fleet, and we don't want to pollute our test data with known unrepresentable data points. Finally, we might want to have something like a dashboard-like counter, because cars that speed too often are offenders, and we need to be very careful. Why would a specific car go that fast that many times? So we might have a threshold, and we want to keep an eye of cars going beyond that threshold, right? Now I go back to Kafka and to lenses, right? And I'm going to, you can see that there is no topic. I'm going to create it straight away. I just created a topic with the structure that we discussed. Notice that it has 5 partition and a factor of replication of 2, just to show. That doesn't really matter right now. And so at the moment, this topic has been created, but you can see that it has a structure that I just mentioned. There is no data. Fine. This doesn't prevent us to start creating our processor, right? Because as I mentioned, the processor is about reacting to data. It doesn't matter, it's not there yet. So to create the processor, you go in SQL processor. Notice that we are in Kubernetes mode, which means that when this processor that we are about to create is deployed, it's going to be created and deployed in Kubernetes. So we can scale up and down within a Kubernetes cluster, and each runner will have its own pod, and the communication between each runner is ensured to be consistent, because each runner will create its own consumer group, and it's using consumer group semantic to create a subcluster. So that's why we can scale up and down, and the rebalancing will just work. So let's create this first processor. Let's say that I'll call it like this, and for now we're going to have 3 runners. I just select the namespace, a Kubernetes namespace. Now I'm going to paste the query, because writing by hand would take ages. And I'm going to go through the details of this SQL in a minute. But the point here is I have written my nice and cool query. I created a processor. Now I can actually click create new processor, see something coming up, but no, wait, it stopped. Why didn't it work? Reading the error, you can see that it says that there is an unknown field. There are actually twice unknown fields, long, and the available fields are lat, long, and ID. what is this about? It's actually about the fact that I wrote sensor long here, rather than sensor long. So it's a typo. And the fact that the engine is typed and it uses the fact that the data is has a schema, we can catch this ahead of time, saving resources, saving debugging time, saving people effort, and we just save ourselves headaches. So now that I fixed it, hopefully this will work, and it does. So a processor has been created. Notice that, first of all, it's actually not running. It's not running right now, and that's perfectly fine. Because running something in Kubernetes takes resources, so you really want to be sure that you want to start it by clicking Start. Now, the runners, as I mentioned, it's going to be 3. This is the query. And another thing that I want to point out is that the query is interpreted as a graph that shows each and every operation in the order. It's like a topological graph. It's a topology. And you can see that it tells you what the query does. Each node tells you what the query does. For example, you see that from car speed events, which is our input topic, we read into a stream, we filter some data, map it, and here we use the result of this in 2 different ways within our query, because we write to 2 output topics in a separate way by reusing this part. So you can see that this is already quite useful to understand what's going on. So let's go through the actual SQL that we are using. There is a lot here to process. So first of all, this is our input topic. So we read this input topic as a stream, remember, a record stream, not as a table. We read it as a stream, and we start shaping the output in one way or another. Here we want the key of the record, the key of the output record, to be a struct with a sensor ID and the car ID. Therefore, we read the topic and we project it onto the key. Another thing is that we wanted to save a Google search to our European colleagues. So we create a substructure called speed with 2 fields, miles per hour and kilometers per hour, with the corresponding conversion. We then wanted to have a flag saying whether this car was speeding or not, and assuming speeding is 55 miles per hour. And you can see here that I'm using a full-fledged expression here. In this case, it's a case, but it could have been an arbitrarily nested expression, and therefore it means that the engine supports arbitrarily nested expression, which is a very powerful tool. Finally, you can see that I'm filtering out the records that I mentioned that we didn't care about. We have some test cars, in this case just 1, and we want to filter it. And we also want to filter things that don't have both a latitude and a longitude. Therefore, I'm filtering these out. And in light of that, these fields can now be made non-nullable in my output, because I know they're not null, because null ones have been filtered. So all this sub part of my query is up until here. Right? Now, I gave it a name, events reshape. Mind you, this is not creating any state. It's not actually creating intermediate topics or anything like that. What do I do with this? I do 2 different things. One, I actually just write it to an output topic, ensuring that the key is stored as other. And that's this branch. And at the same time, I want to create that dashboard-like structure where I keep an eye on cars and their speeding attitude. So what I'm doing is I'm reading from these events reshaped, selecting only the things that have speeding true. I'm grouping by car ID, because really we care only about car ID right now, and we count how many occurrences of this happen, right? And finally, we apply a further post-aggregation filter, saying if these occurrences are bigger than our threshold, in this case 1, then emit this value, right? So this will have all records of things that sped more than once. So, okay, so this processor is now explained. I can start it, and you will see that it starts creating runners. They go green, things that they have deployed. In Kubernetes, we have 3 pods. There is a consumer group, a cluster created between them. Again, no data though yet, because I didn't produce data. Let me fix that. So what we're going to do is that I'm going to create and write events straight into the topic. A bit artificial, but this is a demo. So notice, first of all, that some of these rows have nulls, and some of these rows are for test cars. So we would expect, for example, that these rows will not appear. These are 18 rows, and I insert them. I inserted 18 rows, and now we really want to see that something happened in our processor. And you can see that the metrics already show that something has been happening. Whether it's the right something or not, we can see, but you can see that something has been happening. These metrics come from Kubernetes, from the runners, right? And you can see that the runners have produced different amount of records, because each runner will have a subset of the partitions of this topic. Right, so let's see if the output is the correct output. We had the first topic, car speed events reshaped. We said that some results should be filtered, and we expect, in fact, that 6 of them have been filtered, an output of 12. And indeed, we have 12 records. And you can see the structure is the one that we cared about. We have a key that represents a sensor ID and a car ID, and the value is a structure with a speed with 2 subfields and location with 2 subfields, and the flag, the Boolean flag. And if I change the view, it's a little bit more visible. You can see that the flag is true just where the speed in miles per hour is bigger than 55. So this is false, and this is true, right? Now, this was the examples of this part. What about this? Did that work? So we can check it on the other topic, which is called repeated speedings. We just run it, and we see something interesting. We see, first of all, we notice that we see car 3 with 2 occurrences, and car 2 with 4 occurrences. So car 2 is really bad. We need to figure out why. And also, we see that we have a record with car 1, but no value. I'm not going to go into too much details here, but this is the expect situation. We see the offenders, and this is basically saying downstream car 1 has been filtered out because it doesn't actually meet the criteria. The criteria that car 1 doesn't meet is the fact that it's not bigger than 1. And a group by creates a table, and the table uses nulls in the value section to communicate deletion downstream. Therefore, here, this is what we expect. Car 1 had 1 speeding, but only 1. Therefore, downstream, they will not see that one. They will see a key, but with null. And whatever reads it and knows that upstream there is a table will know how to interpret it. Right, so the thing worked fine. If we were now to insert more data, you would see this number. Yes?
Before we move on, we had a couple questions from the audience.
Yes.
Actually, from Jeremy. The first one is, when creating a table, does the schema get published to schema registry?
That's a very good question. Let me actually show you. Well, we create a table as opposed to stream. In practice, when we create a topic, that will be published to the schema registry. Every time there is a write in Kafka, the underlying topic, if something creates a topic, there will be a schema registry if that topic is using Avro. The thing is, internal topics in K-tables, for example, are not really visible to lenses per se. So you will not see it in the Explorer. And therefore, it's not like we are registering it. That is Kafka streams. What lenses is registering specifically is the schemas for both tables and streams of the topics that we are creating.
Cool. Another question from Jeremy. When writing the 2 topics, is the data read twice?
Sorry, can you repeat that?
when writing to two topics, is a data read twice?
No, that's a very good question as well. So no, absolutely. That is actually the whole point of having this section kind of named like this. It's just like reading a variable. The recipe to read it from one topic is the same for both. It's just that then the output of this step is kind of sent to two different places. But no, the data is read just once. And I'll tell you more, if it doesn't actually create two different kind of concept streams within the internal topology, it creates only one, and it adds multiple nodes on the top, on the outer edge. So this is important because if instead of being a stream here, which is a stateless thing, this was a table, this would have created internal state. If I were to add further steps, if I wasn't reusing as much as possible, then I would actually copy data, concretely copy the Kafka data, and that would be bad for performance and resources. So no, we don't read multiple times.
Thank you, Matteo.
Cool. So where was I? Yes, one final. So basically, the behavior is what you expect. What we expect. It's working fine. A couple of final things. I just want to show you that, as we mentioned, talking about scaling, for example, say that we realize that our 5 partitions are actually very, very reasonably well distributed, but very big. We have a huge amount of rows, and therefore we can increase the amount of runners from 3 to 5. Of course, it doesn't make sense to have more runners than the partition that you're reading from. And in our case, we're reading from one topic. So it really doesn't make sense to have more than 5 runners. And you can see that the runners are being spun up, and they have been spun up to 5. These 2 are the new ones, because you can see they haven't processed anything, and they won't process anything because there is no new data yet. Finally, I can obviously stop the processor. It's going to take a second because it needs to kind of kill the pods and wait for them to actually disappear. And as soon as that happens, I can actually delete the processor as well. So this is kind of like the full life cycle of a processor. One final thing I will mention is that the topics that we created, you can notice that, so first of all, the schema is what we mentioned. So for example, the events shape has the schema that we saw in the data, saved also in the schema registry because it's Avro topics. But one interesting thing about the repeated speedings, the result of the aggregation that is a table, you can notice that this is a compacted topic. We created this topic compacted automatically because this is a result of a table. It doesn't make sense not to compact the table because it's in fact maintained as internally as a topic that is compacted. So it would be wasteful not to have a compacted topic. So we create it as a compacted topic. Of course, this behavior can be overridden for some reason if the user wants to, but by default, this topic is going to be compacted. Right, so this is pretty much all I wanted to go over. I will conclude with just a slide for references, some documentation of the streaming SQL that we have in the processor. The concepts page is especially interesting. Some practical examples and tutorials in our knowledge base to do like end-to-end, from start to end scenarios back at home. And this is another thing I wanted to mention. We have my great colleagues, Fan and Stelios, are going to have a webinar about app deployments on Kubernetes and how Lenses does that on the 23rd of October. And it's an open webinar. So if you are more curious about this, how we work it, what's the security, what's the model, how the secrets work, and all that stuff, please do attend. You will not be disappointed. And finally, any question, doubts, whatever, find us on Slack in the community. And if it's specifically for streaming SQL, the channel.sql channel is for you. Now, again, question.
Before we get into questions, I just want to thank you, Matteo. That was really, really well done. I thought really, really good presentation, and I think you're going to regret that because we're going to use you in marketing materials from here on out. So,
oh, damn.
So that was excellent. So, guys, if you have any questions, either the mics are enabled, you can turn yours on and ask it, or just put it in the chat.